All right, ready to get your hands dirty? You know that word, subnetting? If it's ever felt a little intimidating, you've come to the right place. In this explainer, we are going to completely ditch the dry theory and turn this into a practical skill. We're going to crack the subnet code step by step. Let's jump right in.
So, what's subnetting really all about? Well, at its core, it answers one really important question. Imagine you've got a giant, wide-open office building that's just one huge, chaotic room. How do you create separate, organized apartments in that space? In the world of networking, that's exactly what subnetting does for us. It's the tool we use to bring order to the chaos.
So this is what we're aiming for. We start with one big network address space, and our job is to slice it and dice it into smaller, much more manageable subnets. You know, each one could represent something totally different. Maybe one is for the sales department, another for engineering, or one for the entire second floor. It just keeps everything neat, organized, and way more secure.
Okay, you ready to get started? We're going to kick things off with a classic Class C network problem. Just think of this as a good warm-up, a way to build up our skills and confidence before we get to the heavy stuff. Here is our first mission. You've been handed the network 192.168.1.0 with a /24 prefix. Your task is simple. Split it into 4 distinct subnets. So how in the world do we actually do that? Well, the magic behind all of this is a concept called borrowing bits. See, in any IP address, part of it identifies the network and part of it identifies the device, or the host. To create subnets, we literally just borrow a few bits from the host side of the address and give them to the network side. That makes the network part longer, which is what creates our new subnets.
But how do we know how many bits to borrow? That's where this simple but incredibly powerful formula comes in. 2 to the power of x equals the number of subnets you need. And that x, that's just the number of bits you need to borrow. This little formula is the key to everything.
Okay, so for our problem, we need 4 subnets, right? So we need to solve 2 to the power of what equals 4? Well, that's easy. 2 times 2 is 4, so x has to be 2. That means we need to borrow exactly 2 bits from the host portion. See? Not so bad.
So what does that actually do to our network? Well, our original network prefix was a /24. Since we borrowed 2 bits, we just add them right on top. So 24 plus 2 gives us a new prefix length of /26 for each of our shiny new subnets.
And boom, just like that, here they are, our 4 brand new subnets. Do you notice a pattern in that last number? It jumps from 0 to 64 to 128 to 192. That's not random. That's our magic number, and it's the direct result of the math we just did. It defines the boundaries of each subnet. And with that, congratulations, you've successfully subnetted your first network.
All right, warm-up's over. Time to level up. We're moving on to a much larger Class B network. Now, you're probably thinking, oh great, a bigger network must mean a whole new set of rules, right? Well, nope. I want you to really let this sink in, because this might be the most important thing you hear today. That process we just learned for a small Class C network, it is exactly the same for big Class B networks and even huge Class A networks. The numbers get bigger, sure, but the method, the formula, the logic, it all stays the same.
Okay, so here's the next challenge. You're now in charge of a much bigger network. 172.16.0.0/16. And the requirements are bigger too. You need to carve out at least 80 subnets from this thing. Don't let the big numbers intimidate you. We're just going to apply the exact same process.
We go right back to our trusty formula. We need 2 to the power of x to be greater than or equal to 80. So let's just try some numbers. Let's see. 2 to the power of 6, that's 64. Close, but that's not enough subnets. Okay, let's try the next one up. 2 to the power of 7 is 128. Perfect. That's more than the 80 we need, so we're good to go. That means we need to borrow 7 bits.
And just like we did before, we take our borrowed bits and just add them to the original prefix. Our original was /16. We add the 7 bits we just borrowed, so 16 plus 7 gives us our new prefix of /23. The process is identical.
Now, this table shows you the single most important trade-off in subnetting. As we borrow more and more bits, look what happens. The number of subnets we can create goes way up, from 32 to 64 to 128. But there's a price. Look at the number of hosts you can have in each subnet. It gets cut in half every single time.
For our solution, a /23, we get 128 subnets, but we're left with only 510 usable hosts in each one. It's always a balancing act between more networks and more devices.
Okay, you've seen the method, you've seen it in action on 2 different network classes. Now it's your turn. Let's do a quick pop quiz to really make sure these concepts are locked in for good.
All right, first question. You've got the network 172.30.0.0/16. You need 100 subnets, but here's the catch. Each one also needs to support at least 500 hosts. You're going to have to use that trade-off logic we just saw. Feel free to pause and work it out.
Question 2 kind of flips the script on us. This time, I'm giving you a specific host address and its prefix. Your job is to work backwards and figure out which subnet it belongs to. This is a very practical, real-world skill.
And for our final boss question, we're combining a few skills. Given this host, first find its subnet. Then, calculate that subnet's broadcast address. That's the special address that's used to send a message to every single device on that specific subnet. Remember, it's always the very last address in the range. Take your time on this one.
And that's our workout. We focus a lot on the how, the mechanics of the calculation, but the real skill of a great network engineer is understanding the why. So now that you have the tools, I want to leave you with this question. How would you use them to design a network that isn't just functional, but is truly efficient, secure, and ready for whatever comes next? That's where the real art is. If this explainer helped you crack the code, hitting that like button and subscribing really helps us keep making more. Thanks for watching.